Hey YouTube, Wobbles on a lot here with part 2 of why interstellar space travel and colonisation is never going to happen. It's for DE, who, he's dead now, but never mind. He did ask me to make a movie about it.
Now the Daedalus model, that Project Icarus is the successor project to, Daedalus had a mass of 55,000 tons. So that's 55 international space stations, with a large amount of that mass actually being in the form of fuel. Now, based on that vast amount of mass, it's possible you could construct it in segments, in pieces, and then launch them into space. However, from our analysis, it makes more sense to actually construct it in space from the materials that are more readily available. So in the example of Daedalus, I'll keep going back to that because Project Icarus is ongoing. Going back to Project Daedalus, most of the mass, as I said, was fuel, but it was in the form of a very rare fuel, rare on Earth, called helium-3. And there was good reasons for choosing that fuel. It's one of the most energy-dense ways you can extract energy from fusion. Now, because it's so rare on Earth, you have to go somewhere where it's more abundant, and that's out into the gas giants, the outer planets. So you would mine the outer planets for helium-3. So that was a lot of the incentive or the motivation for the Daedalus actually being constructed in space.
And of course it logically follows that if the best place to construct an interstellar spacecraft is in space, then we're going to have to get a whole lot better at moving around and doing things in our own galaxy before we think about moving on to another. Mark Millis is the founder of the Tau Zero Foundation, an organisation not unlike the 100-Year Starship project. He's also a former head of NASA's Breakthrough Propulsion Physics project. So where does he rate the potential of thermonuclear fusion?
Well, it is an option on the table whose further study would improve our understanding of the situation. At this point, it is really too soon to pick any favorites because, well, let me put it this way. In 3 different studies, one done by looking at the amount of energy available, one done by financing, and one done by technology, all of them came in that it's still going to be about 2 centuries before we could do a serious interstellar flight. So even if you pulled off the technology for a fusion rocket to develop the infrastructure to mine enough helium-3 to fuel it, is still going to take a very long time. In other words, you could make the technology, but to have the amount of energy to put into it takes even longer than developing the technology. And then there's the whole aspect of antimatter rockets, which is another step up in energy densities. Catches there is the amount of usable energy from antimatter is less proportionally. So the ideas that have looked at antimatter have looked at using antimatter to control a nuclear fission or fusion reaction. And the last category, all in the line of within the laws of physics as we know it, is to use sails, solar sails, where the sunlight can just beat off of a large structure and push it along, or to amp that up a bit by shining microwaves or high-powered lasers against the sails to push them even more energetically. And even though those schemes are very simple in principle, and sails have already flown in space and shown that, yes, indeed, they work, to ramp those up to the power levels for doing timely interstellar flight, you're back into the realm where you need huge space infrastructure, and again, kind of like the 2-century thing to bring it to fruition. Now, all that said, all the ones I've just talked about are just technology based on the laws of physics as we understand it. That doesn't mean that that's the only physics we're going to have between now and the next 2 centuries. So another part of what we look at, and this is what the NASA Breakthrough Propulsion Physics project looked at, is what further advances in physics do we need that might circumvent those limits, like propellantless space drives that just use the interaction between the vehicle and its surrounding space, or warp drives and wormholes, which distort space-time enough to where you have faster-than-light shortcuts. Those are also things that are being looked at, although still a short explanation of the status of that. We're not far enough along to know if these kind of breakthroughs are achievable, and if so, how to engineer devices to make them happen.
So, fuel and speed are issues, but so too is design. Because when you think about it, if you're hurtling through the universe at the sorts of speeds already discussed, even a fleck of space dust could make one almighty dent. Richard Abusi again.
There are a wide number of architectures for interstellar spacecraft. One of them is a world ship that would take tens of thousands of years to get there, a generational ship, a hibernation ship, where the inhabitants are placed in a state of suspended animation. But really what you're referring to and what Project Icarus is all about is a rapid interstellar transit. And to get to the closest stars on timescales of a human lifetime, you're going to need to be traveling, or the spacecraft is going to need to be traveling on the order of about 10% the speed of light. So that's about over 18,000 miles per second. So it's incredibly fast. And you hit the nail on the head. I mean, there's not much in the way of space junk when you get into interstellar space, but just the odd dust particle. And there even though the density is very, very low, these microscopic dust particles, if they strike your craft effectively at a relative velocity of 10% the speed of light, it can do absolute horrendous things to the integrity of your spacecraft. So the shielding is a critical issue. So what they did for the Daedalus, they actually had this idea of sending out a kind of a dust swarm in front of the spacecraft that would essentially have a sufficient cross-section so that it would capture any incoming dust particles which would vaporize before impacting the Daedalus. We're looking at a range of other possibilities as well. For example, we're looking at the possibility of using graphene, which has only been used in very minute and small amounts at the moment. But it's supposedly this wonder material with extremely high strength properties. So that's one of the things we're analyzing, if it has sufficient properties that it could protect a vehicle moving at about 10% the speed of light. Other things you can do as well is minimize the cross-section. So instead of having a spacecraft that's quite wide, you could have something that's very long and very thin. And again, that minimizes the cross-section. And what that means is it minimizes the amount of times you're going to bump into these dust particles. So these are all some of the things that our team is looking at.
The crew of the International Mission to Mars has finally returned to Earth in Moscow, bringing one of the world's most grueling scientific experiments to a close. 6 volunteer virtual cosmonauts saw daylight today, in fact about an hour ago, for the first time in 520 days. That's how much time they had to spend isolated in their spaceship Mocha.
The very fact that a small team of pseudo-space explorers could spend more than 500 days in a pretend spaceship simulating a flight to Mars proves that humans can actually spend quite a long time together in a confined space without killing each other. When the Mars 500 team emerged from their mock space capsule in a Moscow research facility, they didn't actually look all that worse for wear. But 520 days is nothing compared to the enormous amount of time it would take to get to another star system, of course. And understanding the psychological dimension of long-term space travel is yet another major problem that will need to be addressed. Mae Jemison from the 100-Year Starship project concedes the psychological issues are huge.
I think one of the things that's really also very interesting about this is that you have to figure out how to get people to interact with each other well. So imagine that you solved all the mechanistic problems that were associated with this travel. You figured out how to do radiation shielding. You figured out the energy equation. You get people there in 20 to 30 years. And so you figure out how to even build this huge ship that you can dump 10,000 people on. But what happens in terms of the behavior and the structure and the political systems and whether or not people actually continue to get along, that they're mentally healthy, stable as they're traveling? One of the biggest challenges is, again, to keep people from trying to design every step of the way right now, because we don't know. And as soon as you start saying, I know the answer right now, then you're probably going to cut off other avenues. There's something that I would say when you talk about how daunting this is and whether or not people say that it's not possible. It's a term that I first heard associated with movies, and that term is suspending disbelief. At some point in time, we have to move forward by suspending disbelief. We have to say for just a second that I believe I can fly, right? We have to suspend disbelief of not being able to fly. Otherwise, we would not have airplanes now because it was a truism that people can't fly. That was known, right? So somebody had to suspend disbelief long enough to allow it to happen. And what we have to do right now is to suspend disbelief long enough that we can actually get to the capabilities that would allow us to go to another star.
Mae Jemison from the 100 Years Starship Project. And one of the guests today were Professors Gregory Benford and Ian Crawford, Dr. Richard Obusi, and also Mark Millis from the Tau Zero Foundation and formerly of NASA. Next week on Future Tense.
Okay, there we go. Well, I deliberately broke that down into 2 segments so I could have a bit of a rant at the end. And they've covered a lot of the ground. I would have to say that anybody who tries to compare colonising another planet with, say, the British colonisation of Australia in the 1700s, they're dreaming. They've got their head in fantasy land. Captain Cook and Arthur Phillip did not have to engineer to carry or manufacture the air that they breathed when they travelled from the Great British Isles halfway around the world to Australia. If you go off Earth and try and colonise some other place, you have to carry your own air or make it on the way. And even though Captain Cook and Arthur Phillip were literally going to the far ends of the earth, they weren't planning on spending 100 bloody years getting there, were they? So the comparison of how the technological revolution conquered the excited states of North Americana with bloody railways, that's bullshit too. And in both cases you've got the Europeans who flogged their own homeland to death, who are out of resources, and they show up with a slight technological advantage in a concentration of numbers on one spot, and they show up planning on thieving the soil, the plants, the animals, the minerals, everything which exists in a land that's being operated by other people who have managed their land better and conserved their resources, and therefore they still had fish in their rivers. They still had fruits on their trees. They had trees in their forests. They had grazing animals aplenty. But, you know, the Europeans didn't. And to try and somehow cobble together the Captain Cook, Arthur Phillip, Jim Bowie meets Hiawatha fantasy with Arthur C. Clarke's Let's Go Visit the Bloody Stars, it's just crap. It's complete bullshit. Civilisations do not colonise other worlds. If they're really bloody lucky, bacteria and viruses do. When you get an asteroid hit blowing a lump of rock with a bacteria inside of it out of one planet's orbit and into another planet's orbit. That's the only way to colonise another planet. Start with a bacteria and an asteroid. By the synchronicity which proves that God theory isn't bullshit, the current Air and Space Smithsonian magazine that I'm reading, which is January 2014, it has in fact an article on interstellar, right? And what it says over here is, there are some serious scientists and engineers looking at this issue because they're dedicated to the idea of interstellar travel, says Les Johnson, a physicist, science fiction writer and editor, and deputy manager of the Advanced Concepts Office at NASA's Marshall Space Flight Center in Alabama. It's not some hobbyists in their garage. There's no serious funding, but a lot of us continue to meet, gather, publish and work on this stuff in our free time. At the turn of the century, Johnson led a project that was one of the first to actually pay researchers to study the idea of interstellar travel, and one of the first drivers, along with a similar effort at another NASA centre, of the current increase in interest. He was managing NASA's efforts to link spacecraft with tethers when the agency began looking for a stretch goal, evaluating whether it was possible to send probes or people to other stars. I was the new guy in the group and it sounded exciting, so I raised my hand and said, I'll do it, Johnson recalls. For about 2 years, I had the coolest job title in NASA, Manager of the Interstellar Propulsion Research Project. Johnson's team determined that the most practical path to the stars was via solar sails, which required fewer scientific breakthroughs than fusion-powered nuclear engines or exotic propulsion methods like warp drive. Ultra-thin sails would use the faint but constant pressure of sunlight or high-powered lasers to propel them to a few % of the speed of light. NASA plans to launch a 120-foot solar sail called Sunjammer after a sail in an Arthur C. Clarke novel in 2015, although it will stay well within the bounds of the solar system. Sail ships are the only way we know to get to velocities that are anywhere close to the speed of light, like 2%, 4%. Gregory Benford, another physicist and sci-fi author, tells the Starship Congress attendees, "Yet even with this relatively reasonable-sounding technology, the problems are so vast that we won't be sailing to the stars anytime soon," Johnson says, that to propel a craft to Alpha Centauri, the nearest star system, a solar sail would have to be as big as the state of Alabama and would need a millennium, 1,000 years, to travel the 4.3 light-year distance. Change the power source from solar radiation to terawatt-scale lasers and you could cut the travel time to a century. Still got to be the size of Alabama. The big drawback? Such a system would require the power, quote, equivalent to the total output of humanity today to run the lasers. And that neatly encapsulates the challenge of travelling to other stars. Even if the science allows it, the engineering demands are monumental, the energy requirements are stupendous, the distances unfathomable, the timescales, well, pick your own adjective. To understand the scale of the problem, consider that the most distant spacecraft yet launched, Voyager 1, recently exited the solar system 35 years after it left Earth. At that rate, if the probe were headed toward Alpha Centauri, but it's not, it wouldn't arrive for another 75,000 years. And there he is, Les Johnson, holding an ultralight aerogel in front of a picture of what he thinks a solar sail might look like. Whereas over here, giving human scale to the twiddly little thing that they haven't been able to fly yet, we see where they're at the moment. So, Space Cadets, it is my melancholy duty to inform you that owing to the nature of space, time and reality, the constraints of engineering and power sources available, nobody is going anywhere. You can't run away from the mess that your ancestors and yourselves have made on planet Earth. You're just going to have to live with the consequences. So maybe it's time to stop shitting in the nest. We're looking at trying to terraform Earth at the moment. Forget about Kim Stanley Robinson's delusions of going to Mars. Terraforming Earth. Trying to make Earth more like Earth used to be instead of the way it's headed, which is the way Venus is now. Seriously, if we contrive to cross the methane tipping point and give ourselves a seriously runaway greenhouse effect, I can't see any serious reason why we shouldn't emulate Venus's atmospheric conditions in, say, 50,000 years. Just at a guess, off the top of my head, pluck the figure out of my arse. Be as insulting as you like, but we're in big trouble, fellas. And you can't run away. You can't do the Captain Cook trip and, make a mess of England and then run around to Australia and pat yourself on the head for how well you're living on somebody else's resources, which is what my ancestors have done. Come to think of it, anybody who claims that advances in human ingenuity and technology have solved every problem we've ever had in the last 5,000 years, they're full of bullshit. The Babylonians didn't solve the fact that they invented salination with their invention of irrigation with underground water. They just made a fucking desert and pissed off and stole Greece's resources. The Greeks didn't solve any problems when they deforested their islands, they just pissed off and stole the Italian peninsula. The Romans didn't solve any problems. When they made a mess of where they lived, they just stole everything that Europe had. The Europeans, did they solve anything when they overpopulated? Oh, be fucked. Christopher Columbus went and pinched the Americas, and Captain Bloody Cook come and stole Australia. Who was it who pinched Africa for him? Yeah. We're not going to another bloody world around another sun in another galaxy far, far away. That's all crap. Unless you wait till you're dead. Once your immortal soul no longer needs engineering support for a life support system, and once time constraints of a human lifetime on planet Earth are no longer a part of the equation, yeah, once you're an angel or a disembodied spirit or a ghost, that's when you can go and visit another star. That's my analysis of the situation anyway. So, DE, wherever you are, go and have a look at life around another star. Warbles on a lot to YouTube. Ciao.